I think the origin story behind this is more challenging than the implementation of it. But this is where we put boundaries of integration into our integrals. So you're not just finding an indefinite integral just in a vacuum. You're finding a definite integral over an integral. So from 0 to 2. That's where we start talking about the accumulation of area. And this is the tie-in to the technology assignment. So if you do have some time and you want to look at that, it's not the worst idea in the world, but I'm definitely going to go over it in class on Monday. All right? That's going to give you the technical background, origin story behind these rules and shortcut rules. All right? But basically, it's telling us that if I have an antiderivative over an interval, I'm just going to integrate the expression, pop in the two boundaries, and subtract. All right? It's just top minus bottom. So antiderivative, let's say I have something like f of x equals x squared. On the interval of 0 to 2. So it's all that's telling me to do is take the antiderivative of this guy, which would be 1/3 x cubed, and we're going to evaluate that over the interval of 0 to 2. That vertical line, if you're not familiar with that, anytime you see a vertical line, it means such that. Okay, it's just shorthand math notation. So 1/3 x cubed such that the boundaries are 0 to 2. All right. So that's telling me to plug in a 2 and then a 0. And then subtract. So we're going to get 8/3. All right, that better be something that you've seen before. Otherwise, I'm not really sure what anybody's doing in Calc 1. Oh, I didn't want to lock this. Whatever, let's see. What you may not have seen is the nifty calculator shortcut to doing this. Because, again, depending on your teacher. So, in your home screen in your calculator, it's just so beautiful. If you've never seen this before, it's another one. Go into your home screen and hit Math 9. Most of you seen it before. Otherwise, it would have been like, oh my God, they're so incredible, you're so awesome, we love you. So all you have to do is just make this look like that, and it'll get you to this. All right. That'll address the fundamental theorem part 1. Part 2 is a little bit of a different story. Gives you that. You want it in fraction form, math frac that bad boy. 8/3. All right. So limitations. The only limitations are your imagination. Some transcendental functions. They can have an issue with this. So anything that maybe is not algebraic, sometimes they have discontinuities, and if there's a discontinuity on whatever interval, the calculator is going to give you an answer. The problem is the calculator will not have thought this through, and so it'll give you an answer, but it won't be the right one. Right? So you'll have to really think about the continuity and differentiability. You know that little throwaway topic in Calc 1, where it's like, okay, here's continuity, here's differentiability. Now that you know that, we're never going to talk about it again. It's so hugely important here, because if you don't know the continuity of a function, then you're going to get wrong answers. Back in the day, it was calculator will give you an error, and you'll say, oh, error, I must have done something wrong. Here, it's not going to give you an error. It'll just give you the wrong answer. But you'll think it's the right answer, and you'll be so happy until you get your test back. So that definitely consider the function that you're putting in. Right? The second part of the fundamental theorem, it's a little chain ruling, but basically it's telling you, if you just look at the model, it's disgusting, but it's telling us that if you have a function as a boundary, the upper boundary is a function, then what you would do is take whatever the function is that you're integrating, replace it with the function that is the upper boundary, but then multiply it by the derivative of that upper boundary. Right? So that's a lot. Let me show you in a quick example. And you'll see it's not really that bad. So, view, zoom, 200, extreme close-up. Extreme close-up, whoa. Movie reference, quick. You guys are the best. No. '90s movie. Early. What's that?
Extreme close-up?
Extreme close-up. Whoa!
Oh. That one both the Baldwin brothers?
No.
No?
If he was in it, he was a very ancillary character.
It was a comedy, obviously, right?
It was definitely a cop.
Listen, what's it do? Where's my car?
No.
No?
No. Let me see if I have another one. That's inappropriate. Can't say that. There was camera one, camera one. There was. There's so many that like they're not inappropriate enough to make it rated R, but they're too inappropriate to stay in class. That is a good question. Yeah, it seems very not useful. However, if the goal of your integration process is to return a function, this is going to help us do that. So, and we'll address that. I have some work drops that actually spell this out for us.
It's finding the derivative on the antiderivative in a set bound.
On a set bound, but the upper bound itself is another function. So really what we're doing is it's more or less a unit change if you think of functions as being units themselves. So think of it as like converting from inches to centimeters, but instead of inches and centimeters, it's t's and x's. So by integrating with respect to t on a boundary that involves x, I'm now going to get a result that has only x's in it. So that when I differentiate, my new function will be related to x rather than t. So it's kind of like a proportional kind of feel to it rather than a numerical. Right. But again, more on that later. That very good stuff that'll help us really understand what this is all about. But for now, the process is telling us to just take the independent variable that's in the given function and replace it with the upper bound, and then multiply by the derivative of the upper bound. So we found an antiderivative followed by a derivative without finding an antiderivative or a derivative. Right? We just did it with direct substitution. Oh, okay, maybe we did a smidge of derivatives. Right? It was just this guy here, but that was all. We didn't go through the process of integrating and then substituting. So if you want to check this out on your own, you can do it. I don't want to waste your time. But if you want to try it, it's not the worst idea. Just to, prove to yourself that it's actually a thing that's valid. Actually take the antiderivative, plug it into two bounds, simplify, just take the derivative of that answer. You'll see that it is exactly this. All right, it's pretty cool. And also, it's a question on the first unit test that everybody is now going to get right. And I'm very excited about this. All right, so maybe you put a star on that. I don't know. What I'd like you to do before the next class is read through all of this stuff, because I obviously I could take you through it now, but I don't want to. I don't want to. The idea here is for you to try to internalize as much of this, see what you know, and then I'll fill in the blanks for you next class. Yeah, this stuff is going to be very important, so definitely dedicate some time. Flashcards are not the worst idea in the world when it comes to this. All right, so I'm emphasizing this for a reason. It's not a throwaway topic. It is incredibly important, right? And if you've sufficiently internalized that, move on to page 7. All right, and do these problems. All right. We'll go over those next class as if you didn't do them at all, but if you can get a leg up on that, that'll be good. All right. It was Wayne's World, by the way.